researcher at the VMware Research Group. I work on this platform called Corfu. It's a cloud scale consistency platform, at least that's what we've been calling it. And a brief outline of the talk I'm going to give today. I'm going to start by kind of motivating the Corfu work by talking about how distributed systems are built today and how Corfu wants to, or was kind of built to address kind of the issue we've observed with distributed systems being built today. Then I'll follow with what Corfu is. I'm going to go over Corfu's value proposition and kind of a brief overview of the internals of Corfu and exactly how Corfu works, so hopefully you'll get an idea of how the system works as a whole. And then if time permits, I'll go over some advances in Corfu because it's really a evolving system. So to really understand what Corfu is all about, let's kind of take a look at the process of building a distributed application so we can kind of understand the pain points. So when an application developer takes an application and is asked to scale it out, like this, for example, this application here, they probably didn't learn how to do that in school. I certainly didn't learn how to learn that in school. So if I had to build a distributed application, the first thing I would consult would be Stack Overflow and ask how should I scale my application. If you take a look at Stack Overflow, it actually tells you, oh, you should take your data and put it into Cassandra, and Cassandra will partition your data out and all will be well in the world. Now your application can scale independently of the data. If you need to increase your scale, you just need to add more Cassandra nodes. And as an application developer, this is all fine until at some point in time you need to actually operate on data that has ended up on 2 of these Cassandra nodes, which isn't a problem you had before. If you had a single application and a regular database, you might use something called a transaction. And if you consult Stack Overflow and ask how do I do something like a transaction over Cassandra, you might find that you should install something like Zookeeper to take locks on rows in Cassandra, for example. And it doesn't actually stop there. Over time, as your application evolves, developers will want to or will need to add additional tools to kind of restore the functionality that they used to enjoy in their single node systems. So pretty soon your system that you want to scale will actually be littered with multiple tools just to scale out your system and restore the functionality that you had before. And this is actually a complete mess, right? Not only do we have multiple systems that we need to maintain, multiple programmers that want to build on this application now have to learn how to use multiple systems that offer very different guarantees and probably store data redundantly in different forms all over the place. But this is the state of the art today, and I think many of you know if you go out and look at how we build as a community large-scale distributed systems today, this is exactly what we do. So when we built Corfu, we wanted to answer the question, if we built a distributed system from scratch, what would it look like? And Stack Overflow doesn't quite have the answer yet. But kind of a hint, all these applications are really building kind of these these logs internally. So maybe there's a way we could stitch that together and consolidate all of them. Okay, now that we've kind of gone over what the state of the art in distributed systems are, let's take a look at Corfu and how Corfu can maybe make the state of the art better. So this is Corfu, guys. This island is going to change the world of distributed systems as we know it. Okay, maybe not quite. But I'm sure many of you are familiar with another Greek island here that has really changed the world of distributed systems, and that's the island called Paxos. So not the island, but the algorithm. The reason our system is named Corfu is actually because Corfu is an island that's quite proximate to Paxos, and we think that Corfu provides many of the same kind of guarantees that Paxos does. And for those of you who aren't familiar with Paxos, I'll kind of give a brief overview. Now, Paxos is a very complicated protocol, despite what some papers might say. And I'm not going to go over the details of Paxos, but I'll try to explain the core of what Paxos provides, which is a kind of a primitive called consensus. And so I'll illustrate that by example. So here we have a system, and its sole purpose in life is to store the value of A. And we can send the system some messages, like we can tell the system to set A to B1. So this is pretty simple when you just have a single system, right? But if you have multiple systems, it turns out that in a real distributed system, you have asynchrony. So when I send the message to set A equals 2, all of a sudden that message might not reach all of the systems at the same time. And it kind of gets worse if I have multiple users trying to modify this value of A at the same time. So if I have this kind of malicious yellow guy trying to change A, now if I stop my system, it's actually really hard to tell what the correct value or the most recent value of A was. And this is exactly the problem that Paxos tries to solve. So the way that Paxos solves it really at a very high level is it basically builds a kind of a distributed log over these nodes. And basically now as an application, I propose commands to this log. And if I stop the system at any point in time, I can kind of inspect which values are at what position. So now I have kind of agreement over these values. And that's actually a very nice property, and it's actually used in many systems today, like you might be familiar with the Google Chubby work. And the problem with Paxos is really that it doesn't scale very well. So when people try to use it in production, they realize that with just 3 nodes, it can maybe do 10,000 operations per second on a good day. And as you add more and more nodes, Paxos starts slowing down because it's got to send messages to all these nodes, which is quite expensive. So Corfu is about taking a look at, this distributed shared log is a kind of a nice property. We can build interesting systems on top of it that are strongly consistent. So how do we take Paxos and really make it scale out? So here's Corfu at a very high level. So what we observed when we built Corfu is that if we separate out basically the control mechanism in Paxos that's really ordering the proposals in Paxos and the data path in Paxos, which is responsible for storing the values in Paxos, we can actually get very high performance. So I know it's a pretty high-level diagram, so I'll kind of go over the components of Corfu right now. So we basically broke Corfu up into 3 sort of entities. The first one is an entity called a sequencer. Now, instead of going to all the nodes in the Paxos-based system and trying to figure out what the correct ordering is, a single entity is responsible for ordering these entries in the log. There's also a component called layout service, which simply helps clients find where the rest of the components in the system are. And next, so that's all part of the control plane. And the rest of the system is is basically a fast data path. just simple storage units that store the data that's presented to it. And I'll show you how this all works in a second. Let's go over some of the properties of the system first. First is that the sequencer, which just issues positions in this log, is actually very fast. It can issue these sequences at over 600,000 operations per second. And it's not part of the I/O path. So unlike the Paxos system, unlike in Paxos, when you have a value, you don't have to give it to the sequencer. You actually write directly to these data units. Next is that this system is scalable. So if you want to add, scale out the system, all you have to do is add more storage units to the system. And a good way to think about this is here I have basically abstract diagram of a log. And as you append to this log, you actually write to different storage units. And you know exactly which storage unit to write to based on its position in the log. So for example, here I have 6 storage units. So the first write would go to this first storage unit, and write number 6 would go back to this first storage unit again. And as you can imagine, I can add more and more storage units, and the only bottleneck I have is this sequencer I had before. The next property is that Corfu is fault tolerant. So, we use a mechanism called chain replication, and each one of these stripes in this log are actually backed with multiple storage units. And that allows us to tolerate, F+1 failure, or with F+1 failure replicas, we can tolerate F failures. And finally, the log gives us very strong consistency. Just like in Paxos, basically the log has a complete order that everyone has agreed upon, and we use that to build strongly consistent systems on top of it. So, okay, I kind of gave you kind of a whirlwind tour of Corfu, but I find that the best way to kind of understand how this whole system works is just to go right in and understand how writing to Corfu would work. So, in the previous system, we talked about, I showed an example where a user might want to propose a new message, a new value to the system. So here, some clients to the system is proposing that A should equal to 2. Now, in a Paxos-based system, you would normally go and send a message, multiple rounds of messages to your replicas. So in Corfu, the first thing that you do as a client is you go to this layout service. And what this layout service does is it basically tells you where all the other servers in the system are. And this is, very importantly, this is a call that you do exactly once. Once you know where all the servers are, you don't actually need to figure out where the servers are again, unless something crashes and then the system reconfigures itself. Okay, so once you know where all the servers are, now you can go communicate to each component in the system. So in the next step, the client will talk to this sequencer and obtain a sequence number, which is the sequencer's purpose. And the sequencer will tell it the next address is at 0. So the client now just writes to the next storage unit mapped to this address. And it knows this via a very simple mathematical projection, which I explained earlier. Now the storage unit has stored the value 2 at this address. And as a client who wants to read that value, I can just go directly to the storage unit because, again, I know that that address 0 lives at this green disk, and get that the value A is equals to 2. And of course, we support many concurrent operations. So we could have many clients talking all at the same time, proposing multiple values. So for example, this next client is going to set A equals to 6. It's going to talk to the sequencer, get the next address, and because it knows from the layout that the next address is going to, that address 1 belongs to this yellow disk, it'll write to this yellow disk and store this value. And you can imagine we could have multiple clients interacting. So this protocol is very nice because as a reader, you don't actually have to communicate with the sequencer. The sequencer is kind of out of the I/O path. I never tell the sequencer, hey, A equals 2, where do I put A equals 2? I just obtain this sequence number, which is implemented as a very fast counter, and go and write this value, which in practice could be potentially very large, right? It could be megabytes directly to the disk. Another very nice property of Corfu is that if I want to know what the most recent write is to the system, the sequencer has all of that information already. So if I wanted to know, hey, what's the most recent value of A? I can actually talk to the sequencer, ask, when was the last time this, what was the most recent value that was written that somebody tried to write? And the sequencer will tell me, well, somebody last tried to write, to address 1, and that's the last token I issued. And it does this without, the sequencer does this without knowing what the value is. But as a client, I can go and now read address 1 and get the most recent value of A without having to scan through this entire log. So far, so good. But storing a value for A is not super interesting. If I want to build a real system or kind of a database out of this, I want to probably actually store different values. So the next slides, I'll actually show maybe a value B being stored. And this actually gets more interesting. So we're going to augment the sequencer that we have to actually keep track of the most recent values for each of these objects, A and B. So when a client goes and asks to write B, it actually tells the sequencer, hey, I want to write B somewhere. It doesn't have to tell it the value of B. It just needs to say, hey, I want to write B. And the sequencer will issue it a token for B. And so here, the most recent write to A was address 1. The most recent write to the most recent write to B is to address 2. Now, the cool part is now since everything is on a single log and not partitioned out, things that like modifying these objects at the same time, which if you remember from before is actually a hard thing to do in a partition system like Cassandra, is actually very easy when we have this log, right? So in fact, all I have to do is write a single entry that says A equals 1, B equals 9, and now at the single address, both of these objects change kind of atomically, which is a really nice primitive to have. And that's without taking any locks in the system or really doing anything outside of the standard Corfu protocol, which is very nice. But so this transaction is actually very, very simple, right? And it's not very interesting. So what if we had a more complex transaction, like one that contains a conditional? So this transaction is going to be a lot more interesting. It actually the client actually wants to only modify B if A equals 1. And the way Corfu executes transactions like in this form is that it computes a read set and a write set. So, and it tells the client, or the client executes this transaction optimistically, meaning that the client has some value of A and B. This log is kind of changing underneath it. So what it does is it first executes if A equals 1. So the client, in its world, already read A, and it last read A at address 3. So it stores in its read set that A was 3. And then it writes, and then it looks at the next statement, which is B equals 7. But instead of writing B equals 7 to the log, it saves it to its write set. So the next step here is now the client computes this read set and write set and sends this transaction off to the sequencer, but only the read sets. And the sequencer will look at its the current addresses that it has, and they'll say, okay, A hasn't actually changed since, and no one has tried to write to A, so you can go write your write set. I don't care what the write set is, you can go write it. And now B is equal to 7. So we kind of have a much more advanced transaction happening here without any locking again. And let's examine a different case. Let's say another client came in and wrote A equals 8, which would actually, it caused this condition to be incorrect. And now the client doesn't know that A equals 8 yet. The log is kind of growing asynchronously. So it's executing this transaction thinking that A is equal to 1. So what will happen here is that the client will go to the sequencer and say, hey, A was 3. I read A at 3. But the sequencer will say, oh, no, actually, you can't write because A is 4 now. And as a result, the transaction will be aborted. The client will retry, and it'll go and read A equals 8. It'll get the correct value, and we'll move on. So this allows us to have very simple transactions with very high performance and without sacrificing any consistency. And that's a pretty powerful construct in Corfu. So looking at all that, you might be thinking, well, how does Corfu compare to other systems? Maybe you've heard about distributed shared logs before. So Paxos, as we discussed earlier, is a distributed shared log. And the way Paxos works is that every single replica in Paxos kind of shares the same log. So in Corfu, we take that concept of a log and we just shard or partition every single address in the log to different logging units. And that lets us scale out without sacrificing the consistency that Paxos gives you. And another system that you might have heard the distributed shared log term from is Kafka. So Kafka does something very different. It partitions data into something called topics. And each topic kind of grows on its own individually. And the big difference between Corfu and Kafka is that in Kafka, if each one of these topics contained objects like A and B, as we discussed before, if I want to do something that like the transactions we talked about in Corfu, because everything is not on the same log, now I can't easily do or kind of create these transactions anymore because I partitioned these logs out separately. So hopefully that kind of gives you a guide to the world of distributed shared logs. So Corfu is about more than just a distributed shared log. We also tried to build a programming model on top of Corfu. To kind of take a look at what this programming model looks like, let's take a look at these two, I guess they're supposed to be routers. So if you are a distributed system programmer and your system contains some routers, you might create a simple Java class that encapsulates some properties about the state of the router. This is a really, really simplistic model. So I'm kind of going to show you how the Corfu code actually magically takes this code and actually turns it into something that works on top of the shared logs that we just discussed. So, one of the things you'll notice about this switch object is that it contains a piece of state, and in this case, it's whether this switch is turned on or not. And that's precisely the what we're going to capture into the log. So the class also has this function which programmers call to change the state of the switch. So to use this switch in Corfu, there's actually just three pretty simple lines that a programmer needs to write in order to utilize it. The first line is basically some boilerplate code to get a copy of the Corfu library. And the second piece of code is actually code that actually automatically wraps the switch around Corfu, and the system actually, Corfu actually dynamically instruments the logical switch class to redirect any modifications to the state of the object into the log. And the third line here, oops, sorry, I meant to do that, is the programmer actually calling this enable port function. Instead of, because the Corfu library has already re-instrumented this class, instead of going and changing this enabled property to true, what the runtime will actually do is it will write enable port true into the log, and it will play back all the most recent modifications to the object before returning and update the state before returning back the control to the user. And what this accomplishes is that if we have multiple clients that are trying to access this object, which they've accessed in the same way, now if they execute the same set of code, they'll actually all arrive at the same state, because before they make any changes to the object, that change will get recorded into this log. And before any function gets returned to them, that object will be updated to their most recent state. So I guess we could also talk about this. Some more advanced work we've been doing with Corfu includes supporting multiple objects. So in Corfu, we have first order support for multiple objects. So like before, you might want to store the objects A, B in the system. And it turns out that something that you will want to do if you have multiple objects is that you'll want to actually find where B is and find where the B's are and find where the A's are. And usually in a kind of a log-based system, that requires kind of scanning through this entire log, which could be pretty expensive if your log is really long and has a lot of different objects. Most systems that have to deal with something like this do something pretty standard. They kind of index the entries that contain B and contain A, and if you want to find where all the B's are, you go and consult the index. But this is pretty expensive, and also making sure that your indexes are up to date is not a super, is kind of a painful operation. So in previous work, we developed a system called backpointers. It's pretty simple. Basically, every single entry contains a pointer to the previous entry. So all the A entries contain pointers to the previous A entries. And this system is great unless you want to read all of the A entries, which is actually a pretty common operation when you want to find the state of A. So in this system, you would have to do 4 separate reads, which turns out to be pretty expensive. So we actually modified Corfu based on recent work to actually make a pretty simple change to the way we replicate. So before, we replicated using this simple replication protocol called chain replication. And as you saw before, that just meant, like in this example, all the even addresses went to one set of storage units, and all the odd addresses went to another set of storage units. We actually realized that we could make a very small change to the way things are replicated. You see, when people talk about replication, it's kind of ingrained into your mind that, oh, I want to replicate, so I should make exact copies of everything. But then we realized, oh, actually, if we kind of just changed the way we replicate a little bit, we could actually build this index, for free, basically. And I'll kind of show you how this works. So what we actually do is we have 2 layers of storage units now. The first layer is going to be the same. It's going to be by address. And that allows us to easily find addresses in this log like before. But the second layer will be by object. So I'll have a storage unit that's dedicated to objects that are A objects, and a storage unit that's dedicated to B objects for illustration. And in addition to writing to the address, now for every single A, right, I also write to one of these this A storage units. And at the end of all of this, all the A's end up on a single disk and all the B's end up on a single disk, and I still get the kind of scalability that this log gave me from before. But now if I want to find all the A entries, I can find them all on this storage unit. So that was a pretty good innovation. So Corfu is actually something we're trying to use within VMware. So in VMware, you're probably familiar with our product that we have called NSX, and we're looking at actually using Corfu as the backing store for NSX. And kind of the way we envision it, and the reason I gave a switch as an example is that, that we're going to take the existing Java model that NSX uses and basically redirect that onto Corfu. And that's an ongoing project, but the goal is to actually, yes?
What is NSX?
Sorry. NSX is a software-defined network product that VMware sells. Yes. So, I mean, yeah. So it's a software-defined network product that manages hypervisors and connects hypervisor switches together. So NSX has a database basically that stores the properties of all these switches and configuration data. And the plan is to actually store these on top of Corfu instead of their existing system. And the reason that Corfu is attractive to them is that it does provide this strong consistency that other scale-out systems don't really provide. We also, so if you remember this from before, diagram from before, have a project called OneData, which plans to take all these different interfaces that programmers are used to and map them onto Corfu. So you can imagine having a Cassandra interface that instead of writing to a Cassandra server actually takes those requests and funnels them into this Corfu log. And if you have, what these systems are basically doing is generating logs on their own. So if you can consolidate all these logs into a single entity, we could reduce a lot of storage overhead, and we could also take data that's represented in Cassandra one way and present it another way in MySQL. So that's the OneData effort. So finally, we are an open source effort. Yes, we're on GitHub, and no, it's not a source code dump. We're actually very dedicated to try to making Corfu really a production-ready kind of system. It's not there yet. We have 51 open issues, and it's quickly growing as people are really using it. But we've already dedicated a rather large team to really making sure that Corfu really gets used both within VMware products and both hopefully outside of VMware products. So you can check out the source code today. You'll probably run into some bugs, but it's also an active project that every day is seeing new commits. So it's not something that we just wrote a paper about and dumped the source code on the internet. It's actually something that we're trying to make something that people can use. So, and you could take a look at it and see if the object models change how you see distributed systems. So that's my talk.
Thank you. Could you explain what happens, how you recover from sequencer failure, please?
So that's a very interesting situation. Let's jump back to a slide with a sequencer, hopefully very quickly. Okay, so when the sequencer fails, what happens is that clients notice that they can't talk to the sequencer anymore, and they go and find this layout service, which elects a new sequencer. In the original version of Corfu, if you go and read the papers, it actually turns out that the sequencer is not a safety requirement. It can actually hand out completely wrong tokens, and the system will work, but not very performantly, because basically, the storage units that we have guarantee that once you write to an address, that address can never be overwritten. So if I write to address number 1, the storage unit has promised that nobody else will write to 1. So it's actually the storage units that are enforcing the safety guarantees of Corfu.
So the writes are immutable?
Yes.
And it's append only?
Yes. Yes. So yeah. So this layout service just brings another sequencer up. Ideally, it has the most recent address that the log wrote to for performance reasons. Yes.
How do you deal with the holes and slow clients? So if a client gets a sequencer that's a sequence that's far in the future, what happens to the existing ones if a client crashes before we're actually writing the commands?
Right. So we have a mechanism called hole filling. It's pretty simple. Basically, if a client acquires a sequence number and doesn't write within a specified amount of time, another client can actually go in and safely write just junk to that entry. And when that slow client, let's say, comes back up, he'll try to complete his write, but there will be a hole there, and he'll have to retry with a new sequence number. The consequence is basically that there could be a lot of these hole entries, so we have a process that goes and collects those hole entries and compacts the log.
I was actually going to ask about compaction. So does this just grow forever, or what's the process for
right. So
shrinking the log?
Yeah. Yes. So yeah, that's a very important question. In the case of these objects, where we're not storing any history, every once in a while you might want to checkpoint this log, a pretty standard mechanism. So there is a garbage collection process that basically goes and scans the log, and when the application, at some application requested rate, takes only the most recent, or captures the state of these objects and writes the most recent state into the log. You can think of it as condensing all the entries into a single one.
Sorry, a couple of questions. One, what happens when you reworked how stuff was stored on disk, your new version, you end up with all the copies of a particular object on a single disk. Hasn't that just destroyed your redundancy?
Oh, so this is actually, well, no, it has not, because actually it turns out that A is on this unit and also scattered across these units.
Okay, so
right.
it can recover from any sort
so
of failure.
yeah, so it's actually nice in terms of recovery, right? Because I can actually scale my recovery out to all these nodes on the top.
Okay.
Because the data is spread out across them.
And my other question was going to be, to what extent have you done any formal verification of the properties of Corfu?
That's an interesting question. We don't have a formal model for Corfu, but we are working on building to do model checking over Corfu. So that's, yeah.
Hey, I enjoyed the talk, and especially about the Replex stuff. I have been following the project on GitHub, actually.
Okay.
So I see all the commits roll in and all the comments and stuff. But I was curious about the object store, which seems to me, I guess I would call that a materialized view of kind of the state of an object.
Yeah.
Does-
So yeah.
I mean, is that a fair characterization of
Yeah.
what
So you could think of A and B, this stuff on the top as a materialized view. Yeah.
Does the Replex storage also use chain replication, and it goes
It's
through this
kind of
compaction process?
Yeah,
or-
it's kind of a variant of chain replication, right? So you can think of Replex as generating dynamic chains. So 0 is actually a chain that's predicated on what object was written to it. So which means that in order to get the full chain, you actually need to know that A was written to that. Yeah, but yeah. Does that answer your question?
Any more questions? Right. Let's thank our speaker.